Welcome to the course on risk modeling in insurance. This video covers the basics of modeling severity data in an insurance setting. Now, before you dive into the actual material, please keep in mind that the lecture sheets of this part of the course are not based on a single source, but combine a bit of the Klugman, Pannier and Wilmot loss models book and the book of Jet Fries, as well as a bit of my own research work. Now, you recall from the introductory lecture that pricing models in non-life insurance require a model for both frequency as well as severity. You already worked with frequency models in the previous videos, and you will now continue with severity models. Now, when modeling severity data, keep the principle of parsimony in mind. That is, you will choose for the most simple model that adequately reflects reality, where the meaning of adequate depends on the purpose of for which the model is used. Now, throughout the lecture sheets, you will move from simple to more complex models, and as Klugman, Pannier and Wilmot denote in their book, no universal agreement exists on certain definitions that will matter here, and the sheets typically follow the definitions and specifications of the Klugman, Pannier and Wilmot book. Moreover, it is not possible to cover the whole universe of possible loss models, so we'll make a thoughtful selection in this set of lecture sheets. Now, in this video, I will use the names losses, severities, and claim sizes as synonyms. And typical features of loss data are the following. They are usually positive, they are skewed to the right, and they have a heavy right tail. So let's start with having a look at some examples of loss data as they are exposed in the insurance literature. So first of all, I here mention a data set on Danish fire insurance losses, where we have about 2,000 losses above 1 million Danish krone, which were registered during a 10-year period from 1980 to 1990. And those losses have been used in a long series of research papers. In this univariate loss dataset, you see the following features of the loss distribution. So you see their visualization with a time series plot over time, so where each of the bars indicates the size or the height of the loss. You see their density plotted over here, and you see their empirical CDF and some fitted cumulative distribution functions of certain models that have been calibrated to the data. You see that over here. Now, another famous dataset is the car insurance dataset provided by the General Insurance Association of Singapore, which was studied in a series of papers by Professor Jet Fries and Professor Emile Valdez. 3 types of losses are registered in this dataset. There are losses on an own damage cover, a third-party property cover, and a third-party injury cover. The density plots over here on the right-hand side illustrate the skewness of the data and illustrate their long right tail. So these are typical features of insurance loss data. Now, as promised, you will start with simple parametric distributions useful when building models for insurance losses. And a parametric distribution is a set of distribution functions determined by one or more parameters, the number of parameters being fixed and finite. Well-known and useful examples in our setting are the exponential, the log normal distribution, the gamma, the inverse Gaussian, etc. Keep in mind that typically multiple parameterizations of these distributions are around, and you should review carefully which specification, which parameterization you want to use when, for instance, calibrating your model to data. Now, the table here gives you an overview of loss distributions typically used to model small to moderately large losses in a risk modeling context. You find here both their density and the mean, as a function of the parameters used in the distribution. Now, functions related to the exponential, the gamma, and the log normal distribution are provided as part of R's standard library. And for each distribution, you have 4 standard functions available, where the D refers to probability density function, the Q refers to the quantile function, C is for the cumulative distribution function, and R is for simulation. Distributions that are slightly more exotic, such as the inverse Gaussian distribution, may require the installment of additional R packages, like the statmod package or the actuaire package, in order to have similar functionalities available for these more exotic loss distributions. Now, continuing with examples of such more exotic loss distributions, let us first mention the Burr distribution. This is a 3-parameter distribution that can be obtained as the result of a continuous mixture, as explained at the bottom of the sheet. Having 3 parameters, this distribution is more flexible than standard 1 or 2 parameter distributions, but it may also be more difficult to calibrate this distribution to a given data set of insurance losses. The generalized beta of the second kind, with acronym GB2, is another flexible loss distribution, popular when building flexible risk models. This distribution has 4 parameters and contains many other distributions as limiting cases. That is, when you put one or more of the parameters in this distribution to specific values, the GB2 distribution will simplify to some other named distribution. You can see this GB2 distribution as a family of distributions. Now, in the software R, you can use the Burr and the GB2 distributions within the actuaire package. Examples of papers where these distributions are used for risk models in insurance are listed over here. So you can have a look at those if you're interested. Now, as with our discussion on count data, you will typically use maximum likelihood estimation to fit a parametric distribution to severity data. And the main steps involving maximum likelihood estimation are repeated here. So you will collect a sample of observed insurance losses. You will specify the distribution that you wish to calibrate, in this case with parameters θ1 up to θk. You write down the likelihood as the joint density of the observed losses. You maximize this likelihood, or its logarithm, over all possible parameter values. And one way to visually inspect the fit of the model to the data is by comparing its fitted CDF with the empirical CDF. Other tools, like likelihood ratio tests or the use of information criteria to compare the fit of a set of candidate models to a given data set, will be covered later on in the computer labs. Now, when discussing MLE for loss data, you should be aware of the possible presence of truncated and or censored losses. Here you see an example from a disability insurance setting. What matters in a disability insurance setting is the time spent in disability. That is the time that elapses from the onset of a disease to the recovery or perhaps the death of the insured or the end of the policy period. Now, for insured 1, in this example, you see a timeline until recovery. His disability time is therefore fully observed. Typical for disability insurance is that a benefit is only paid to the insured if his time spent in disability exceeds a certain waiting period. For example, in the case of insured number 2, you see that this time spent in disability does not exceed the waiting period. Insured 3, on the other hand, he is still disabled at the end of the observation period, that is at the present moment. So we say that his time in disability is called right censored. Now, the phenomena illustrated on the previous sheet are loosely described here. So the data in this example are subject to left truncation and right censoring. Left truncation refers to the setting where insureds are disabled during the waiting period and are not observed by the insurer. Right censoring, on the other hand, refers to the situation where some insureds have not yet reached recovery, policy expiration, or death by the end of the observation period. So their duration of disability will be above a certain value, but we don't know by how much. So to keep a clear view on the differences between censoring on the one hand and truncation on the other hand, keep in mind that with censoring, we have some information about the dependent variable, that's the outcome variable of interest, but we do not always know the dependent variable itself. For instance, in the disability insurance example, part of the time spent in disability is observed, but this time is not observed in full detail. With truncation, some individuals of a subset of the population of interest do not appear in the sample. For example, in the disability insurance setting, individuals in disability for whom the time in disability does not exceed the waiting period are not spotted by the insurance company. You can find the necessary notational details to work with right censoring in your data on this sheet. So we only cover here right censoring as this matters most in risk models. Let y be the dependent variable or the outcome of interest. For instance, the time from beginning of disability until either recovery, policy expiration, or death. Let C be the censoring time or the censored value. And what you will then observe is C. You will observe the minimum of Y, the complete observation, and C. And you will be able to register with an indicator variable delta whether the observation is right censored or not. So if the observation is not censored, Y and C are equal. The indicator delta is 1 if the observation is right censored, and it is 0 if it's not. Now, in the presence of truncated and or right censored data, you have to adjust your likelihood function to account for the presence of those not fully observed data. And the crucial step here is to distinguish a censored from a non-censored observation. With a non-censored observation, Y, the likelihood contribution is as usual. So that is the density evaluated in Y. And for such observations, the corresponding indicator value, the indicator variable delta, is equal to 0 in our notation. However, with a censored observation, you only register C, and the likelihood contribution is going to be the survival function evaluated in C. This expresses the probability that under the given loss model, the outcome is larger than C. So this expresses the probability that under a given loss model, you will observe an outcome larger than C. That is indeed the only information that we have about a right censored loss observation. That is, that its completely observed loss or outcome will be larger than C. And for such observations, in our notation, the corresponding indicator variable delta is equal to 1. Now, putting this all together, the likelihood of an independent sample with n observations can be written as follows. What you see here at the bottom of the sheet. Rearranging the terms then shows that you have density contributions for the fully observed or the exact data on the one hand, and survival terms or survival contributions for the right censored data on the other hand. So whereas censored observations are available for study, but in limited form, truncated response are a sort of missing data. For example, with left truncation, the outcome Y, the response variable or the dependent variable, is not observed if it is below a certain threshold denoted here with T. In the likelihood, you should handle this by including conditional probabilities and conditional densities. That is, you will use the conditional density of y given that it exceeds an observed threshold t, as indicated here at the bottom of the sheet. So you will use this conditional density when writing down your likelihood for this specific truncated observation. Now, when searching for an appropriate or putting this all together, the likelihood for right censored and left truncated data is given as follows. So compared to the likelihood that we wrote down for right censored data on sheet number 19, you will now work with conditional densities and conditional CDFs, where you condition on the fact that y should be larger than an observation-specific threshold ti in order to take this left truncated feature into account. So that is the likelihood that you're going to optimize in order to estimate a specific loss distribution to a data set where right censoring and left truncation are present. Now, when searching for an appropriate parametric loss model, it is good to have a non-parametric estimator at your disposal of the distribution or the survival function of your losses. And here you cannot work with the standard empirical CDF, as this would ignore the presence of truncation and censoring. The Kaplan-Meier estimator of the survival function offers you an alternative here. And it is recommended to compare the survival function of a fitted loss model with this non-parametric benchmark estimator to visually check its goodness of fit. And if you're interested in learning more about this Kaplan-Meier estimator, you're welcome to find information about it in the literature, and you're also welcome to look up the R package survival, where the Kaplan-Meier estimator is available. So this concludes our introductory video on fitting loss distributions to insurance losses. So we discussed a bunch of suitable loss distributions, and we discussed the phenomena of right censoring and left truncation, and how you should adjust your likelihood function to account for these phenomena.